Hello everyone. So today for my circuit theory assignment, I was speaking about the application of second order circuits in myoelectric prosthetic control systems. So before I talk into the application of second order circuits, I will be talking about the myoelectric prosthetic control system. So these systems, they're biomedical devices that are designed to utilize electrical activity generated by residual muscles. See, these electrical activities, we call them electromyography signals. They're produced by the action potential in the nerves, all right? And usually they're produced when you contract a muscle voluntarily. Now, the central approach, the operation for a for this myoelectric prosthetic control system is to have electrodes and the prosthetic hand, and we obtain EMG signals, we process them, and then we interpret them to drive control over to drive the prosthetic limb. In this case, in this example, as you can see here, we have a surface electrode battery to power everything. We obtain EMG signals and then we process them and then we send a command to the myoelectric hand, either to do something or to do nothing. So before I talk more into the details of how these circuits work, I would like to explain the difficulties in EMG signals. So these EMG signals, specifically the surface EMG signals, as we can see here, this one, surface electrodes, obtains surface EMG signals. They have amplitudes that range in the microvolts to a few millivolts, and they have a broad frequency spectrum from 20 hertz to 450 hertz. All right. The primary challenge in EMG signal obtaining these EMG signals, is the contamination from motion artifacts, which occur due to electrode movement relative to the skin during muscle contraction. As we can see here, if I move my forearm, my skin is going to move, which will affect the readings we get. And another major challenge is whenever I also, again, this example, the forearm example, whenever I contract my forearm to move it, I'm also moving 5 fingers that are moving a lot of muscles in the hand, which means that the frequency, the frequencies for the forearm and the hand, they are all extremely uh, close. They're usually in the same frequency band. So muscles involved in similar or coordinated movements, they often produce signals within overlapping frequency bands, which makes it difficult to distinguish between intended actions using raw EMG signal data. And every single thing that we need to do, or the myoelectric prosthetic hand needs to do, prosthetic control system needs to do, has to be done in real time. So this brings me to why first order circuits are not suitable for this type of system or biomedical device. Because in the myoelectric prosthetic control system, we have we have to get the signals conditioned uh, very correctly. So the first order circuits, they cannot meet the requirements because they only have a filter that contains only one energy storing element, which means it attenuates at unwanted frequencies gradually. As you can see here, the red line shows that we attenuate only at a rate of negative 20 dB, while on the blue line, which represents the second order circuits, we see a negative 40 dB, which allows us to attenuate to low frequency bands much faster. Okay, the EMG signals are particularly challenging, again, because of the noise components, and such as the motion artifact and power line interference. Exist these interferences, they exist close to the same frequency range or band as the muscle signals themselves. So when a first order filter is used, either too much noise remains or the important EMG information is lost during filtering. This is why we use second order circuits, because the one we're going to talk about today for the specific control system is going to be the second order band pass filter design, right? These address the limitations of first order filtering by employing second order band pass filters. So what am I talking about? I'm talking about something that looks like this. It first pass will remove all of the single high pass. For example, here will be the green line. It will remove all of the high frequency noise, and then in the single low pass, it will remove all the low frequency noise. right? And as you can see, when you merge them together, we'll see this beautiful curve showcasing everything. And here, this one, as we can see, we have a filter 1 and a filter 2. Each filter, it's a band pass, so it'll pass through 2. The first filter has to handle the high frequency, the second filter handles the low frequency. We have 2 capacitors in each. These are for the frequencies, and then the resistors set the cutoff point. Anyways, moving on. Second order bandpass filters, it allows us to only to remove all of the high frequency electrical noise and then the low frequency motion artifacts, and keep the needed or the wanted muscle frequency band. Right? In practice, these filters are commonly implemented using active configurations such as the silent key topology, which utilizes an operational amplifier along with resistors and capacitors. This design offers stable gain, high input impedance, and low power consumption, making it well suited for wearable prosthetic devices. The second order bandpass filter is placed after the amplification stage and before the analog to digital conversion. By conditioning the signals at the hardware level, the filter ensures that only meaningful EMG activity is processed by the control algorithm and is processed in real time. Because it's really important that everything is done in real time, because at the hardware level, everything is faster than at the software level. This significantly improves muscle classification accuracy and enables smooth responsive prosthetic movements. Here, this is an example of the silent key topology. And I'd like to conclude by saying that second order circuits are a fundamental requirement for these myoelectric prosthetic control systems due to the complex noise prone nature of EMG signals. First order circuits just simply do not work because they do not provide sufficient frequency selectivity to reliably separate muscle activity from interference, which limits the control accuracy and the system stability. Thank you.